Welcome families. Today we are going to discuss on the types of aircraft engine in detail. Watch until the end. Aircraft engines are the heart of an aircraft, providing the necessary thrust to lift the aircraft into the air and keep it flying. There are several types of aircraft engines, each with different designs, principles of operation, and uses. Next are the main types of aircraft engines and their key differences. Aircraft engine basically classified into 4. 1. Piston or reciprocating engine. 2. Gas turbine or jet engine. 3. Ramjet and scramjet engines. 4. Electric engine. Piston engines or reciprocating engines. Piston propeller engines. The first aircraft engine was a piston propeller engine, developed by the Wright brothers in 1903. These engines dominated aviation for the first half of the 20th century. The piston propeller engine uses a piston to compress air and fuel, igniting the mixture to produce mechanical energy. This energy drives the propeller, which pushes air backward to create thrust. All piston engines operate on the same four-stroke process. Engine and propeller technology and power have improved significantly throughout the years, but today's piston engine types still work much the same way. Generally speaking, the piston engine functions much like a typical automobile engine. By taking in air from the surrounding environment and mixing it with fuel, these aircraft engine types work by burning the fuel to produce heated gas exhaust to move a piston attached to a crankshaft. But the automotive drivetrain uses its crankshaft to turn the wheels of a car. A piston propeller engine crankshaft is directly connected to one or more propellers. It is applicable to small general aviation aircraft. Simple and cost-effective for short-distance flights. Limited speed and altitude capabilities. The arrangement of cylinders in reciprocating engine are inline, V-type, radial, flat or opposed. Inline engines. Cylinders are arranged in a straight line. Inline engines were widely used in early aircraft during World War I and into the early 20th century, especially in fighter planes. Their streamlined shape made them suitable for aircraft where aerodynamic drag needed to be minimized. Inline engines work on the basic four-stroke cycle. Intake, compression, power, exhaust. The engine takes air and fuel into the cylinders, compresses it, ignites the mixture with a spark plug, and uses the explosion to drive the piston down. The movement is converted into rotational force that drives the propeller. It is used in small aircraft where space and aerodynamics are important. Compact and streamlined. Limited power-to-weight ratio. V-type engines. The V configuration of cylinders, usually 8 or 12, offers compact design and balances the weight distribution. Like inline engines, V engines follow the four-stroke process but with the cylinders working in an opposing sequence to provide smooth power output. Cylinders are arranged in a V shape. More compact than inline engines for the same displacement. It has higher vibration compared to radial engines. Radial engines. Radial engines were very popular from the 1920s through the 1950s, particularly in military and commercial aircraft. Their robust and simple design allowed for easier maintenance. Radial engines have cylinders arranged in a circle around the crankshaft. Each cylinder fires in sequence, causing the crankshaft to rotate. Radial engines are air-cooled, making them well suited for aircraft where liquid cooling would add weight and complexity. High power-to-weight ratio, reliable cooling due to air exposure. Bulkier design and more drag due to the large frontal area. Opposed or flat engines. These engines are common in light aircraft and have been used since the mid-20th century. Companies like Lycoming and Continental are major manufacturers. The horizontally opposed cylinders provide balance, minimizing vibration. The pistons move in opposite directions, driving a central crankshaft. This type of engine is air-cooled and very efficient for small aircraft, where weight is a concern. It is compact and light, minimal vibration. Lower power output compared to more advanced engine types. Key differences in piston engines are power output, cooling, complexity. Varies by configuration, with radial engines generally providing more power than inline or flat engines. Radial engines are better cooled than inline engines due to the exposure of all cylinders to the airflow. Radial engines are more complex in design compared to inline and opposed engines. The parts of piston engine. 1. Cylinder block and cylinders. The cylinders are where the combustion process occurs. The number of cylinders varies based on the type, inline, radial, V-type, etc. Typically made of aluminum or steel to handle high temperatures and pressure. 2. Pistons. The pistons move up and down inside the cylinders. As fuel combusts, the expanding gases push the piston down, which turns the crankshaft. Typically made of lightweight aluminum alloys for durability and heat resistance.
3. Crankshaft.
Converts the linear motion of the pistons into rotational motion, which drives the propeller. Made of steel or forged alloy to handle the mechanical stresses.
4. Connecting rods.
These rods connect the pistons to the crankshaft. They transmit the motion of the pistons to the crankshaft. Made from steel or alloyed metals for strength.
5. Valves and valve train.
The intake and exhaust valves control the flow of air-fuel mixture into the cylinder and the exhaust gases out of it. The valve train operates these valves. Made from heat-resistant alloys, usually with hardened surfaces to withstand wear.
6. Camshaft.
Controls the timing and movement of the valves, ensuring that they open and close at the right time in the engine cycle. Typically steel or cast iron, designed to last for the life of the engine.
7. Spark plugs.
Ignite the fuel-air mixture in the cylinders. Ceramic and metal, with electrodes that create a spark.
8. Carburetor or fuel injection system.
Mixes air with fuel in the proper ratio before it enters the cylinders. Modern engines may use fuel injection instead of carburetors for better efficiency. Made from lightweight metals or alloys, depending on the type.
9. Magneto and ignition system.
Generates the electrical spark needed to ignite the fuel-air mixture. Consists of an electrical coil and a magnet to generate current.
10. Lubrication system.
Provides oil to lubricate moving parts and reduce friction and wear. Oil pumps, filters, and various channels to distribute oil throughout the engine.
11. Cooling system.
Most piston engines are air-cooled, using fins around the cylinder to dissipate heat, though some larger engines may use liquid cooling. For air-cooled systems, fins are typically integrated into the cylinder design. For liquid cooling, radiators and pumps are used.
12. Governor.
Regulates propeller speed by adjusting the pitch of the blades to maintain constant RPM. It is a combination of metal gears and hydraulics.
Jet or gas turbine engine. The first one is turbojet engines.
The turbojet engine was the first type of jet engine ever developed. The turbojet was the first type of jet engine developed, with pioneers like Frank Whittle and Hans von Ohain designing early models in the 1930s. The first operational turbojet aircraft were used during World War II. Turbojets work on the Brayton cycle. Air is drawn into the engine and compressed by a series of compressor blades. The compressed air is mixed with fuel in the combustion chamber and ignited, creating a high-speed exhaust. This exhaust is expelled through a nozzle, producing thrust. Applicable for high-speed military aircraft, early commercial jets, example Boeing 707. High-speed performance, especially at high altitudes. The drawback is inefficient at low speeds, high fuel consumption.
Turbofan engines.
Turbofans were developed in the 1950s to address the inefficiencies of turbojets. Turbofans add a large fan at the front of the engine, which pulls in more air than turbojets. A portion of the air bypasses the combustion process and is directed around the engine core, providing additional thrust while improving fuel efficiency. The air moves through two parts of the engine. Some of the air is directed into the engine's core, where the combustion will occur. The rest of the air, called bypass air, is moved around the outside of the engine core through a duct. The bypass ratio of a turbofan engine is the ratio between the mass flow rate of the bypass stream to the mass flow rate entering the core. High bypass ratios provide the high thrust needed for acceleration and climb during takeoff while also maintaining required thrust levels for high-speed cruise. The engine combines the advantages of a turbojet with the quieter, more efficient operation of a propeller engine. Turbofan engines combine the best features of turboprops and turbojets to create something better. The objective of a turbofan engine is to achieve a higher level of thrust and performance while maintaining the same level of fuel consumption. A turbofan engine can produce large amounts of thrust while remaining relatively quiet, even at lower speeds. For these reasons, this type of aircraft engine powers the vast majority of commercial airliners. Turbofan is similar to turbojets but with a large fan at the front, which directs air around the engine core. The disadvantages is bulkier and heavier than turbojets, performance drops at very high speeds.
Turboprop engines.
Turboprops emerged in the 1940s and 1950s as a hybrid between piston and jet engines, designed for aircraft needing fuel efficiency over short to medium distances. Turboprops use a gas turbine engine, similar to a jet engine, to drive a propeller. The engine burns fuel to generate high-pressure gas, which spins the turbine. The turbine is connected to a propeller via a reduction gearbox. This allows the engine to deliver high torque at lower propeller speeds. Most of the larger aircraft you'll see with a propeller use a turbine-based engine. The turboprop engine is a turbine engine that directly connects to a gearing system to turn a propeller, much like a traditional piston propeller engine. Turboprop engines are highly fuel efficient at low to medium speeds and rotate at a mid-range speed airspeed. It is limited to lower speeds and altitudes compared to pure jets.
Some part of turboprop engine are 1. Propeller.
Propeller converts the rotational energy from the engine into thrust by moving air. Made from lightweight metals, example, aluminum alloys, or composite materials. Some older designs used wood.
2. Reduction gearbox.
Reduces the rotational speed of the turbine so that the propeller can spin at an optimal rate for thrust generation. Aircraft reduction gearbox is a component of transmission system placed along with shafts for reducing the speed of the input from the motor, while also multiplying the torque the input creates. Made of hardened steel or high-strength alloys to handle torque.
3. Engine core.
The engine core in a turboprop works similarly to that of a jet engine, with a compressor, combustion chamber, and turbine. Materials used are high-temperature alloys, similar to those used in jet engines.
Turboshaft engines.
Developed in the mid-20th century, turboshaft engines are a variation of turboprops, optimized for helicopters and other non-fixed-wing applications. Similar to turboprop engines, turboshaft engines convert combustion energy into mechanical power, but instead of driving a propeller, they drive a shaft that powers helicopter rotors or other machinery. Most commonly used to power helicopters, a turboshaft engine is very close to a turboprop with a few minor design modifications. Rather than a propeller, turboshaft engines are designed to turn a transmission, which in turn is connected to the helicopter's rotor system. The biggest advantages to these aircraft engine types are their small dimensions, low weight and high static performance, allowing them to climb to extremely high altitudes. All jet engines operate on the Brayton cycle, using the compression and combustion of air to generate thrust. The bypass ratio, which is amount of air bypassing the engine core, distinguishes turbojets from turbofans. Key differences in jet engines:
Fuel efficiency, speed and altitude performance, noise levels.
Turbofans are generally more fuel efficient than turbojets, especially at low speeds. Turbojets excel at high speeds, while turboprops and turbofans are more efficient at lower speeds and altitudes. Turbofans are quieter than turbojets due to bypassed air. Ramjet and scramjet engines.
Ramjet.
As an airplane's forward velocity exceeds Mach 1, the air pressure generated by the speed of the airflow through the core reduces the need for a compressor. When speeds approach Mach 3.5 to 4, a compressor is no longer required. Based on this phenomenon, the ramjet was invented and patented in 1908 by the French scientist René Lorin. Ramjets by definition need ram air, that is to say, air that is forced into the intake as a result of the aircraft's high speed, thus they are redundant at zero speeds. Consequently, a reasonable starting point for this engine to work is at approximately Mach 3, and they can sustain effective propulsion as fast as Mach 6. Ramjets are very helpful in applications featuring a small, focused, and straightforward mechanism for high-speed operation, such as missiles. A ramjet uses the aircraft's forward motion to compress incoming air, without needing a compressor. Fuel is injected into the compressed air and ignited, creating high-speed exhaust that generates thrust. It is applying for supersonic and hypersonic aircraft and missiles. Cannot operate at low speeds, requires a separate propulsion system to get to operating speed.
Scramjet.
Scramjets are a more recent development. The scramjet aims to overcome the speed limitations of ramjets. The scramjet is an innovation on the ramjet in which the combustion chamber is specially designed to operate with supersonic airflow. Scramjet is simply an acronym for Supersonic Combustion Ramjet. In a scramjet, air is compressed at supersonic speeds, and combustion occurs while the airflow remains supersonic. This allows for hypersonic flight, Mach 5 and above. Ramjets and scramjets are used for high-speed applications, primarily in military and research contexts. Unlike traditional jet engines, these engines rely on the speed of the aircraft for air compression, making them highly efficient at supersonic and hypersonic speeds. The two models rely on the natural ramming of air to produce thrust. The basic operating principle in ramjets and scramjets involves converting the significant kinetic energy of the incoming hypersonic, which is speed greater than Mach 5, or supersonic air, into pressure energy. Electric aircraft engines. Electric aircraft engines are a relatively recent development. The first successful electric flights occurred in the early 2000s, with ongoing advancements as battery technology improves. Electric aircraft engines use electric motors powered by batteries or fuel cells to drive propellers or duct fans. The main advantage is the clean, quiet operation and the potential for renewable energy sources. Main parts of electric aircraft engine.
1. Electric motor.
Converts electrical energy into mechanical energy to drive the propeller or fan. Electric motors are typically made with a stator, stationary part, and rotor, rotating part, using copper windings and steel laminations to create magnetic fields.
Two. Battery pack.
Stores electrical energy to power the motor. Usually lithium-ion batteries, but future designs may use solid-state or other advanced battery technologies.
3. Controller.
It manages power flow from the battery to the motor, controlling the speed and efficiency of the engine. Electronics housed in a protective casing, often made from aluminum or composite materials.
Please like, share, subscribe. Thank you.